Okay. So we'll be dealing with this problem today, and before dealing with this problem, I'll be just again moving towards your flow chart. So flow chart yesterday we have seen. So before that, I'll be telling you about again the methodology with respect to your Newton Raphson. Okay, so today's lecture agenda will be like this. I'll be sharing you with you another one simulation. Okay, so through that simulation, you can see that what how you are doing your load flow with respect to your in your MATLAB you'll be seeing. I'll be just showing a glimpse of it. Okay, so initially, you can just take this. So this is what we have seen in the previous lectures. Okay, we have started with the Newton Raphson. We started with your current flow equation at the various buses, and we have derived at the current. Okay, we have derived at the current, and after that we separated your uh, real power and the reactive power. We have separated it. Okay, uh, we have separated your real power and your reactive power, and after this over here, I want to emphasize a single point. That is, so while expanding this equation, okay. So while expanding this equation, what happened is that you're getting the real power as a summation, right? Whereas the reactive power, not over here. Wait a minute. Yeah, over here for the Jacobian matrix. So for the Jacobian matrix, you're getting the diagonal element to be a summation one, right? Whereas in case of your off diagonal element, the summation is not possible. Can anybody justify why you are not having a, summation in your off diagonal element?
Sir, because the value is y1, for example, y12 means y21, both are equals.
Yes, of course.
Only self-admittance, we will add the in the individual number buses, y12, y13, etc.
Yes, yes, you got the answer right, man. That is for the diagonal element. The what we'll be doing is it is nothing but your self admittance. Whereas your off diagonal elements, it is your transfer admittance. Okay, so with respect to your admittance matrix, here you will be getting summation. That is the number of buses connected to the particular bus. Okay, so your diagonal element there will be summation term. Whereas with respect to your off diagonal element, in generally what you'll be doing for your transfer admittance, for your transfer admittance, you'll be just negating the value. You'll be just so the same thing only over here. So here only just negating it, and then over here we'll be taking a partial derivative with respect to your del. Okay. So that's a point I want to justify. Okay. So after that, we have seen all these things, how the Jacobian matrix is formed, and then we have moved towards with respect to your flow chart and PV, PQ buses we have seen. So the next part is we have to get with respect to your problem only. The another one thing is that this point, this epsilon is there, right? So as I said, this epsilon in some cases, if it is not given, you can assume this epsilon. Okay, so this epsilon value, that is your problem will be more accurate only if this epsilon value is very small. Okay, if they didn't give the value of epsilon, means you can assume, but you can assume in such a way that the epsilon value has to be small. Okay, So based upon this epsilon value only, what happens? The iteration count is determined. Okay. So for this for this thing, I will be showing you the MATLAB model. So you'll be getting the ideology with respect to this epsilon. Okay. So here is a this is a 3-bus system. Okay. So it is a 3-bus system. So I hope we have already seen this system. So it is visible, I think. Whether it is visible, the MATLAB window.
Jacobian matrix itself, we will go when the I value exceeds the I max value, no, sir.
Which one you are telling, man? For Jacobian matrix?
We will go to the Jacobian matrix when the I value exceeds the I max value only, no, sir. Until then, there is no need for Jacobian matrix formation, no, sir.
Yeah, for Jacobian matrix formation, what you have to do is you'll be checking with respect to your del P and del Q, right? So for del P and del Q, it must be converging with respect to the epsilon value. So in yesterday flowchart we have seen, right? Wait, I'll be telling you. So you just confirm with me that whether this MATLAB window is visible.
Yes,
Whether
sir,
it is visible?
sir.
It is visible, right? Okay, fine. So here, okay, I'll be just explaining. So it is a slack bus. So this bus one is a slack bus, and over here there are 2 loads. Okay, so this bus 2, and then followed by this bus 3 are I think your PQ buses. And for here, this corresponds to a slack bus. So these are the entries. Okay, so here the voltage they are giving is 25 kilovolt. So it is rated for a 25 kilovolt, and then the frequency is 60. Okay, so what happens is that so these are all nothing but your admittances. These are all nothing but admittances, and over here I have already learned the load flow solution. Okay, so here you can see this orange color box. So here it is given. It is at 10 power e power 3, 1.05 at 0 degree. So I hope you can get this. Why we are having this as a 0 degree? Because it is a slack bus. Okay, it is a slack bus, and hence you will be getting this to be as a 0 degree. Okay, but whereas in your PQ buses, so here you can see the PQ bus, so you are getting some other angle, the voltage angle, you are getting some other angle, 10 power e power 3. The same voltage is across your bus 2 and bus 3, but the voltage angle is varying, and the per unit value is also varying. Okay, so here you can see the load flow. It is you have to move towards tools and load flow. Okay, so it is for a 3-bus system. So over here you can see here that it is a 3-phase source. Load 2, load 3 are connected. Okay, and over here the consumption of your load 1, the real power, reactive power consumption is given over here. Okay, so after putting compute and then if you are applying it to the model, so you will be getting the changes in the values. Okay, initially there won't be any kind of values. I have already run the load flow, so you're getting the values. So to get a detailed analysis about this, what you can do is you also generate a report. Okay, so you can move to load flow. So here there's a report, right? So if you're clicking on this report, you'll be getting a load flow report. So you can export it to a sheet also. So here you can see, here it is very clearly stated that the load flow is converged at 2 iterations. Okay, it is a simple 3-bus system. So for a 3-bus system, here the convergence is at 2 iterations. And here you can see for your bus 1. Okay, your bus 1 is a what you can say swing bus or the slack bus. The slack bus other name is swing bus. I have already told. So the swing bus over here, it won't be having any kind of PQ load. So here your PQ load will be 0. So the power across your bus 1 and then with respect to your bus 2, it is around 200 megawatt is real power. Okay, next coming to the bus 2. So for the bus 2, your real power is around, it is the real power and reactive powers are given. Okay, load they have given since it is a PQ bus. Okay, but there's no generation as it is a PQ bus. The same corresponds to your third bus also. Okay, so from here, what and all you can infer is that you can infer your real power, reactive power elements you can infer. After that, you can also infer your Z, that is impedance shunt. Okay, that is it is nothing but your Y bus matrix, which is represented in terms of your impedance. Okay, it is nothing but the reciprocal of your this value. You'll be getting a reciprocal of your admittance, you'll be getting your impedance. In the MATLAB, generally, they won't be representing in terms of admittance. Instead, they'll be representing in terms of your impedance. Okay. After this, you can also generate a report if there's any kind of subnetwork. That is, this is with respect to the subnetwork. That is your generation report. So here the generation bus is only your first bus. Okay. If a PV bus is also present, means then it will be coming under this category. So moving on to the PQ load report. So the number of load connected to the particular bus, we can get it out. So it is around 258 megawatt. So and the total power also it gets calculated. And finally, you can get the Z shunt. So with this Z shunt, you can also see the amount of power flowing and each and everything can get it out. So this is with respect to your 3-bus system. It is with respect to a 3-bus system, and it is a very simple network, and hence can see that the iteration is converged within 2 iterations. Okay. So over here, the algorithm over here uses Gauss Seidel only, but in MATLAB, you can also change the methodology to Newton Raphson, like that, and we can change. Okay, so this is for a 3-bus system, and this is a 15-bus system. Here you can see it is a 15-bus system, and for this, what happens is that the iterations count generally will be increasing. Okay, so here you cannot say that all the systems connected are with respect to your load or with respect to your generation part. Some buses will be of generation part and some buses will be of load part. Okay, so it is a very complex, huge network. So here itself you can see each and every part will be connected to some other network. So bus 3 itself, here you can see it is having a very complex interconnection. Okay, and the report generated for this bus is around here it is. So for this also the load flow is converged within 2 iterations. Okay, so the main difference is that over here you might be asking, sir, there it is a 3-bus system, or there also you're asking within 2 iterations it is formed. So here within 2 iterations is formed. So you might be asking. So the thing is that the what we presented with this giving a very optimal solution. Okay, so it's also I think for 15 bus also I think we might have went through Gauss Seidel only, but the thing is it is converged. Okay, but in some cases what happens, this iteration count will be increasing. Okay, if it is not converged, that is while calculating with this powerful analysis, there's a particular epsilon value. So this epsilon value you can change. It is possible that you can change this epsilon value in this simulation itself. So when we are changing in such a format that epsilon value, then generally iteration value increases. Okay, so showing you that practically in some other point. Okay, and now I'll be just I think you might have got some glimpse, and now I'll be moving to your Newton Raphson again. Problem will be again seeing. Okay. So I hope I have given a small glimpse about calculating your load flow with respect to your MATLAB itself. And now we'll be seeing this thing. So this is a problem. I hope you might have taken down. So that is here they have given a single line diagram. So this single line diagram is having generator. So it is having generator at buses 1 and 3. So the magnitude of bus voltage is adjusted to 1.05. Okay, so this is your bus value. It is given in the question. So yeah, they have given the slack bus 1.05 at 0 degree, and the voltage magnitude bus 3 is fixed at 1.04 per unit. Okay, so here the real power generated also they have given the P and Q for the second given. So here the line impedances are not. So here you have to be very, very careful that here they didn't give the admittance value. You have to be very careful. Here they didn't give you your admittance value. They have specified your line impedances. Okay, per unit on 100 MVA. So here they had taken the base MVA. The base MVA is around 100 MVA. Okay, so what they are asking? They are asking to obtain the power solution by Newton Raphson method for this simple circuit. So for this, it is a 3-bus system. So I'll be giving 5 minutes. You just try to form the Y-bus matrix form for this particular thing. So I'll be giving 5 minutes. It is very easy. It is a 3x3 matrix. You can easily form the Y-bus. So you have to be very clear. The given values are in admittance. So the given values are in admittance. So what you have to do, you have to take the reciprocal of each value. You have to take the reciprocal of each value, and then you have to form the Y-bus. You try to form the Y-bus matrix. So after forming the Y-bus matrix, you might be getting the rectangular form. Okay, rectangular form Y-bus matrix. With respect to this NR problem or the Newton-Raphson problem, you have to convert that rectangular form into the polar form. Okay, you have to convert into the polar form. That Y-bus matrix values you have to convert into the polar form. Okay. So try it out fast. Take the reciprocal and form the Y-bus matrix. Okay, I hope you might
The
have
admittance value we
found
need to
it.
change polar forma, sir.
Yeah, that is the entire matrix you have to change. The entire matrix what you have found might be in the rectangular form. So that you have to change with respect to your polar form. Okay. So we just check it out. The right matrix. Okay. So your y buses will be getting around 20 minus 50, then minus I had some network problem, so I'll be continuing it. Okay, so here the Y bus matrix, what you'll be getting is around Y bus. Okay, so it will be around 20 minus J 50. Okay, after this it is minus 10 plus J 20. Okay, so after this it is minus 10 plus J 30. Okay, so after this it is again the reciprocal, so it is minus 10 plus J 20, and over here it will be minus 10 plus J 30, and the diagonal is 26 minus J 52, and over it is minus 16 plus J 32, so it is symmetrical, so minus 16 plus J 32, so the final one is 26 minus J 62. I hope you are getting this Y bus matrix, right? So no confusion with respect to this formation. So you are getting this Y bus matrix, right? Yes or no? Can at least type in the chat box. So you are getting it. So you are getting right. Okay. So for your NR method, you have to convert this into your polar form. Okay. So this entire Y bus matrix, you have to convert it to your polar form. So with the converting it to the polar form, you just take up to 2 decimal points. No need to go for more than. So if it is coming out means you just round off with respect to your 2 decimal points. So you will be getting 53.85 at an angle minus 1.9029. So you're getting this answer. So any doubts? In any discrepancy with respect to this answer? So initially, have you whether formed the Y bus matrix? Say yes or no. Current.
Sir,
Whether have you formed the Y bus matrix? Students, kindly respond. Okay. So now you are just converting it to the polar form. So converting this to the polar form, you will be getting in this pattern. Okay. So after this, what you have to do, convert the second term. So it will be around 22.36 at an angle of 2.03. Okay, and the third one it will be 31.62 at an angle of 1.89. Okay, so for the second row the same thing, these two gets repeated, so it will be 22.36 at an angle of 2.03, and over here it is 31.62 at an angle of 1.89. So after this, for your diagonal element is 58.134 at an angle of minus 1.07. Sorry, 1.10. Okay, 107 it is. After this, it is 35.78 at an angle of 2.03. So the same comes around here, 35.78 at an
I
angle
get
of 2.
different values, sir, when it is converted to polar form. The angles alone is
What, man?
changing. When I convert
angles are-
the yes sir rectangular form into polar form, the angles are coming different for me, sir.
Oh. So anybody else getting this answer, or all of you are getting some other answer? Students, kindly respond.
சார் அந்த ஆன்சர் தான் வருது சார் ஒய் பஸ்.
இல்லை, போலார் ஃபார்ம் மாற்றினீங்களா? போலார் ஃபார்ம் மாற்றினது வந்து எந்த ஆன்சர் வருதுன்னு சொல்லுங்கள்.
வருது சார் வருது.
அதுதான் இப்போ கரண்ட் நீங்கள் மோடு கரெக்டாக வச்சிங்கன்னா செக் பண்ணுங்கள். ஸோ வெதர் த மோட் யூ ஹவ் செலக்டட் இஸ் கரெக்டாக செக். So because if you are keeping even the mode 2 and you are converting to rectangular polar form, there will be some discrepancy in your angle. Okay, so you just check it. Okay, so with this y bus formation, I'll be moving to the next step. That is, over here you might have got the angle for each and everything. Okay, so these angles will be using in your power equations P and Q. Okay, so for that you have to first write your equations. Okay, so here there are two buses. So if you want to just write this, I'll be giving some time. So there are two buses or nodes. There are two buses, or they will be calling it as, okay, and bus 2 and bus 3. So for this bus 2 and bus 3, you have to find, that is yeah, you have to find your P2, P3, Q2. Okay, Q3 you won't be finding since it is a PV bus. Okay, so with respect to this, what you'll be doing is, as per your flowchart what you have seen yesterday, you will be writing the equation first. Okay, so for your PI equation you have to write. So it is summation j equal to 1 to n. Okay, summation vi vj, after this yij, and then it is cos theta I theta j minus del I plus del j. Okay, this is for your PI. So you just put the values. So for your P2, what you'll be getting is, you'll be getting it as V2. Okay, V2 V1. We won't be starting with your first bus since it is a slack bus. Okay, you won't be starting with that, and after this it is cos theta to 1 minus del 2 plus del 1. Okay, this is the first element. So after that it will be V2 square. So your j will be equal to 2, so this will be changing as 2. Okay, so here the I value is 1, and here it will be moving towards 2, so it will be V2. So this becomes a square. V2 into V2, it will be V2 square into y22. Okay, y22. After that it will be cos theta to 2 minus del 2 plus del 2, so this gets cancelled. So I told about this in the while expanding this equation in the previous lecture. So after this it is plus v2, okay, then it will be v3. So it will be coming in a cyclic format. Okay, it will be coming in a cyclic format. So it will be after this it will be y23. After that it will be you have to put cos theta 23 minus del 2 plus del 3. Okay, so this is the equation. You have expanded it, and now you have to substitute the values of your b2. Okay, you have to substitute the value of your v2, v1. So all the values you have to substitute it. So over here uh, question, so here they didn't give mention anything about your, they have specified more precisely about your v3, right? V3 and v1 voltage only they have given, right? And okay, so as they didn't give with respect to your v2, I have already told what you have to do. You have to consider a flat voltage profile. So if you are considering a flat voltage profile, okay, then your v2 value will be equal to 1, since it is not given, and the del 2 will be equal to 0. Okay, hope you might be clear. So now we can substitute those values over here. So your p2 will be equal to, v2 is 1 into, so what is your v1? So v1 value, it is given 1.05 at an angle of 0 degree. So here it will be 1.05 at an angle of 0 degree. And so here we are not speaking about angles, okay? We are using your absolute value. So then y12. So y12 value is y12, you just take the magnitude alone, okay? y12, this value, okay? 22.36. 22.36 into cos theta 21. So theta 21, you have to see it, this value. So theta, this 21 element is this, okay? So theta 21, you have to consider this value. So it is 2.03, okay? So minus, so this del value you have to take 0, and we, for del 3 also they didn't give, so del 3 also you can take 0, and over here the equation will be somewhat big, but what happens is that most cases for the first iteration you will be getting the values as many values, it will be of 0. Okay, so 2.03, so del 1 it is already given to be 0 degree over here. So here you can take it as plus 0. Okay, so after this b2 you have to put, so it is 1 square into y22 value is this value 58.134, okay, that is into 58.13 you can take, okay, 13 you can consider. So after this cos of theta 22. So cos theta 22 is minus 1.1. You can round off 1.11, and over here minus del 2, it is again 0. This just cancelled off, right? So this gets cancelled off, so we'll be getting this value. Okay, so after this plus v2 value is again 1 into, so v3 they have given, so v3 it is given to be 1.04. So y23 is this value, 35.78. Okay, so into cos of theta 23 is this value, 2.03. Okay, 2.03 minus, so del 2 value is 0, and del 3 value is also 0. So since you are taking the flat voltage profile, so del 3 is also 0. Okay, so now we have to solve this equation, and we'll be arriving at P2. Okay, this is for first iteration alone I'm speaking. Okay, for the second iteration, if you're moving out means again you have to do it usually actually this problem goes up to nearly 3 iterations. Okay, um, you just try your level best. I will be explaining the steps. Okay, you just stick on with the steps, and we'll be seeing. Okay, you just solve this equation for now, and with this I'll be closing the class. What value you are getting for P2, and the other part we'll be seeing in the next class. Okay, so for this P2, you can easily put in the calculator. Usually for Newton-Raphson, first iteration is very easy. So if you're going towards your second and third iteration, what happens is that this del value, right? The del 2 value just changes. This del 2 value changes. As this del 2 value changes, the entire P2 value also changes. Okay. So what's the value you're getting for P2?
This one we should we also need to calculate P3 also, no sir? Or there is no
Yes,
need.
man. You have to calculate P3 also. Yeah, initially we have started P2, P3, and it goes on. Okay. Actually, this problem is in your presentation part in the PPT. It is there. Okay. So you just see it here. I'm just substituting and I'm explaining. Uh, you just see the problem is somewhat lengthy, but it is easy to solve only. You just try it out. Okay. After this P2, you have to move towards your P3. Okay, you have to move towards your P3. After that, you have to substitute the formula for your Q. So here we won't be sticking with Q3, we'll be sticking with your Q2, since the third bus is a PV bus. Okay. So if you want to refer the entire problem, you just get towards your PP presentation section. Okay, in the presentation section, I have posted this unit 2 notes, unit 2 PPT. In the unit 2 PPT, you can just come down to the end of the section and you can see the problem. Okay, so you just solve this and you tell me the value of P2 alone, and after that we can just wind up the class. Simple multiplication, pass value. The hang calculator, right? So also students, I have posted quiz for your first unit. That is first with respect to your first CAT exam. Okay, so try to take that quiz also and complete within Saturday. So don't forget Saturday is the last date for completing the quiz. The quiz is for 10 marks, so it is easy only. You can also refer the internet and you can just answer the questions also. Okay. So what's the P2 value you are getting? Normal multiplication only. No, why you are taking so much time? So okay, I'll be stopping it. Okay, so the next class you start, you tell me the answer, and can also refer the PPT what the PDF just in the presentation part. Okay, so you try to complete the quiz within the time. Okay, so many of the students didn't complete the assignment. Two students didn't complete the assignment, I think. One student have completed, but he didn't post it on time, so I have marked as 0 for him. So you have to submit each and everything within the time period, then only the mark will be given. Okay, try to complete it within the time so that the maximum marks will be given. So in the next class we'll be continuing. So thank you students.
0.76 sir.
What are you getting?
118.76 sir, P2.
118 you are getting.
Yes sir.
So it is one. Okay, no problem. You have came near. You'll be getting around 114. You'll be getting.
But I got 118.76 sir.
Okay, we'll be seeing tomorrow. Okay.
Yes.
Okay. Thank you. Thank you.